Welcome back to the Deep Dive, where we cut through the digital noise to bring you the essential insights you need to stay ahead. Think about your day-to-day life. We live in an on-command, on-demand 21st century reality, right? You expect to stream your favorite show instantly, access your banking app anywhere, or pull up that crucial document from years ago with just a click. And here's a wild fact that often goes unnoticed. Individuals are now collectively creating more digital data than even large organizations. Think about that for a second. All those photos, documents, videos, social media interactions. It's a personal data explosion. With this exponential growth of digital information, protecting and instantly accessing all that data isn't just a convenience anymore. It's absolutely crucial, whether it's for your personal peace of mind or for the very lifeline of a business.
It truly is. This ever-growing sea of data, from our personal memories to critical business transactions and vital medical records, absolutely demands robust systems to ensure it's always available, correct, and secure. It's not just a nice-to-have, it's a foundational challenge of modern IT infrastructure. The stakes couldn't be higher.
And that's exactly what this deep dive is all about today. We're giving you a direct shortcut to understanding the incredibly critical and often unseen world of information storage. Our mission today, as part of the broader Backup and Archive module, is to take a truly deep dive into backup in virtualized environments. We're going to unpack the fascinating evolution of backup strategies, explore the clever technologies that make it all possible, and most importantly, understand how the dramatic shift to virtualization has fundamentally changed the game for data protection. It's really a core lesson in building resilient digital systems.
Precisely. We'll look at the fundamental why behind backup, the how of traditional methods, and then specifically zero in on the unique considerations and, frankly, the game-changing solutions that virtualization brings to the table.
And trust me, this isn't just for the folks with IT professional in their title. Whether you're prepping for a big meeting where data resilience is on the agenda, catching up on a rapidly evolving field, or simply immensely curious about what keeps our digital world from collapsing around us, this deep dive offers essential knowledge. We'll explore some surprising facts and key insights, translating what can often feel like dense, highly technical concepts into clear, actionable understanding that you can immediately apply. So you ready? Let's unpack this I. The criticality of information availability. Why we need backup. So we're here to talk about backup, but before we even get to the mechanisms, the how-to, we absolutely have to grasp the fundamental why. And that takes us straight to two incredibly crucial concepts in the world of modern business: business continuity, or BC, and information availability, IA. Can you walk us through what those twin pillars mean in the grand scheme of keeping a business running?
Absolutely. Think of business continuity as the enterprise's overarching strategic umbrella. It's an end-to-end, enterprise-wide process. It encompasses all the activities an organization needs to perform, both inside and outside of IT, to proactively plan for and mitigate the impact of any downtime.
Downtime, planned or unplanned,
Yeah,
right?
exactly. That downtime could be planned or it could be a complete surprise. The ultimate overarching goal of every BC effort is to ensure what we call information availability. It's about ensuring the business keeps breathing no matter what.
Okay, so business continuity is the grand strategy, the big picture. What then, specifically, does information availability mean from an IT infrastructure perspective? Because that sounds like where the rubber truly meets the road.
That's right. Information availability, or IA, refers to the IT infrastructure's inherent ability to function exactly as expected during specified times. We break this down into three core interlocking aspects. First, accessibility.
Getting to the data when you need it.
Simple as that. The information must be available to the right user at the precise moment they need it from wherever they are. Second, reliability. This ensures the information is correct, completely unaltered, and uncorrupted.
So you can trust it.
Exactly. It means what you retrieve is the identical, pristine data that was originally stored. You can trust it. And third, timeliness. This defines a specific window, a particular time of day, week, or even year, during which the information must be accessible.
Ah, so it's not just 24/7 necessarily.
Not always. For example, if a critical online application is contractually obligated to be accessible between 8:00 a.m. and 10:00 p.m. every day, any disruption outside that window, say at 2 a.m., wouldn't technically affect its timeliness rating. But during those core hours, every second counts.
That distinction, especially regarding timeliness, is really illuminating. It highlights that availability isn't just a binary up or down state. With those definitions in mind, what are the most common culprits behind information unavailability? What actually causes the systems to go dark, so to speak, in the real world?
Yeah, this is where many people's assumptions are often challenged. While we tend to fixate on dramatic, catastrophic events, the overwhelming majority of outages are, in fact, planned outages.
Planned, you mean on purpose?
Well, scheduled and anticipated. These are disruptions that are planned. This includes things like installing or integrating new hardware, performing software upgrades, applying critical security patches, and perhaps surprisingly to some, even performing routine backups.
Wait, backups cause downtime.
They can. By their very nature, backups can cause temporary downtime or performance degradation for the systems they are protecting. Other common planned outages include application and data restores, routine facility operations like power maintenance or renovations, and migrating testing environments into live production. Businesses do this to improve, but they carefully schedule it to minimize impact.
That's a truly interesting point about planned outages being the majority.
Yeah.
Well, so if most are planned, what about the unplanned ones? What blindsides organizations?
Unplanned outages are also significant, of course. These typically stem from very human causes. Human errors are surprisingly common.
Oops.
Moments.
Exactly, whether it's misconfigurations, accidental deletions, or incorrect commands. Then there are critical issues like database corruption, which can bring entire applications to a halt. And of course, component failures, both physical, a hard drive failing, a power supply dying, and virtual, a hypervisor crash, or a VM getting corrupted.
Okay, that makes sense.
But what truly might surprise you and contradicts popular perception is that major disasters.
Like floods, fires.
Right, whether natural like floods, fires, or earthquakes, or man-made like large-scale cyber attacks, account for less than 1% of all information unavailability incidents.
Less than 1%. Really?
The everyday issues, both planned and unplanned, are the real constant drivers of downtime.
That really shifts the perspective. And when a business experiences downtime, regardless of the cause, the consequences can be truly severe, far beyond just a momentary inconvenience. What are some of the most critical impacts that organizations face?
Oh, the repercussions are multifaceted, incredibly complex, and can be devastating to a business's health and future. You're looking at a significant loss of productivity, meaning reduced output per unit of labor, equipment, and capital. Employees can't work, machines sit idle.
Right, things grind to a halt.
Then there's substantial loss of revenue. This can be direct like missed sales transactions or more complex, such as compensatory payments owed to customers, future revenue loss from churned customers who lose faith.
Ouch, losing customers.
Yeah, or billing cycle disruptions, or even investment losses if critical market data is unavailable. Furthermore, prolonged or frequent downtime inevitably leads to poor financial performance. This impacts everything from revenue recognition to cash flow, a company's ability to secure discounts from suppliers, payment guarantees, their credit ratings, and even the stock price if they're publicly traded.
It ripples outwards, doesn't it?
It really does. And finally, and crucially, there's severe damage to reputation. This can result in a profound loss of confidence and credibility with customers, suppliers, financial markets, banks, and business partners, leading to long-term impacts that are much harder to quantify and recover from than a simple financial hit.
Yeah, trust is hard to rebuild.
Exactly. In fact, many organizations now calculate the average cost of downtime per hour by summing the average productivity loss per hour and the average revenue loss per hour. It really crystallizes the financial incentive to avoid it.
Wow. That really puts the stakes into perspective. When you factor in all those indirect costs and reputational damage, the numbers can be staggering. So how do organizations actually measure this information availability? Beyond just knowing if the system is up or down, are there specific metrics they rely on for proactive planning?
Yes, absolutely. Two critical metrics are foundational for proactive risk analysis in business continuity planning. Mean time between failure or MTBF and mean time to repair or MTTR.
MTBF and MTTR.
These aren't just academic terms. They're vital for understanding system resilience.
Okay, let's unpack these two. What exactly do MTBF and MTTR tell us, and why are they so important?
MTBF is a statistical measure. It represents the average time a system or a specific component within a system operates normally without any failures between one failure event and the next.
So how long it works before it breaks?
Basically, yes. It's a direct and quantitative measure of reliability, and it's typically expressed in hours. So the higher the MTBF, the more reliable that component or system is considered to be. Think of it as how long you can reasonably expect something to work before it breaks. MTTR, on the other hand, stands for mean time to repair. This is the average time required to repair a failed component or restore a system to full operation.
The repair time.
Well, crucially, this isn't just the actual wrench turning time, it encompasses the total time from when the fault is first detected,
Okay.
through mobilizing the maintenance team, diagnosing the root cause, obtaining any necessary spare parts, performing the actual repair, thoroughly testing the system, and finally restoring data or services to full functionality.
So the whole process from failure to fully back up.
Exactly. It's calculated by taking the total accumulated downtime over a period and dividing it by the number of failures that occurred during that period. The shorter the MTTR, the faster you can recover, which directly improves availability.
So if I understand correctly, information availability, or IA, can actually be expressed very elegantly using these two metrics. How does that formula look, and what does it reveal?
You're absolutely right. IA can be calculated in a couple of ways, but the most insightful one using these terms is IA equals MTBF. MTBF plus MTTR.
Okay, MTBF divided by MTBF plus MTTR.
Right. This formula vividly illustrates how achieving higher reliability, a longer MTBF, and quicker repair times, a shorter MTTR, directly, mathematically, contribute to higher overall availability. It's a clear roadmap for where to invest your efforts in system design and operational efficiency.
And this leads us directly to the concept of the nines of availability, right? Like 5 nines availability, which is often cited as the gold standard in mission-critical environments. What does that actually translate to in terms of real-world downtime?
Exactly. The nines refer to the percentage of time a system is available. So 99% availability is 2 nines, 99.9% is 3 nines, and so on. When we talk about 99.999% availability, often called 5 nines, it means a service is available for 99.999% of its scheduled uptime in a year.
5 nines. That sounds impressive.
It is. When you break that down into practical terms, it equates to only approximately 5 minutes and 15 seconds of total downtime per year.
5 minutes a year. Wow.
Think about that, less than 6 minutes. That's an incredibly stringent requirement for continuous operation, and it means every aspect of the infrastructure must be designed for extreme resilience. Achieving 4 nines, 99.99%, is about 52 minutes of downtime per year, and 3 nines, 99.9%, is around 8.7 hours. So each additional 9 dramatically reduces the acceptable downtime.
That's a serious, serious commitment for any organization. And to even get close to that kind of availability, let alone 5 nines, organizations absolutely have to aggressively address what we call single points of failure, or SPOFs. What exactly is an SPOF, and where might we typically find them lurking in a complex IT infrastructure?
A single point of failure is precisely what its name implies. It's a component or element within a system whose failure can bring down the entire system or disrupt the entire IT service. It's a weak link.
The one thing that breaks everything.
Pretty much. In a typical modern IT setup, these SPOS can exist at almost any layer. For example, a single virtual machine, VM, could be an SPOF if it's not protected. The hypervisor running multiple VMs could be an SPOF. A single host bus adapter, HBA, connecting a server to storage, or a network interface card, NIC, connecting a server to the network, could fail.
Just one cable, one card.
Exactly. The physical server itself, if it's not part of a cluster, is an SPOF. The core IP network, a fiber channel, FC, switch, and a SAN, a specific port on a storage array, or even an entire storage array if there's no replication, all of these can represent single points of failure. The failure of just one of these components, if not mitigated, can render an application or entire business operation unavailable.
So the goal is to eliminate as many of those single points as possible. To do that, organizations employ what's known as a defense in-depth strategy. Can you give us some specific practical examples of how they build redundancy into these systems across different layers, like real-world stuff?
Certainly. Defense in depth is about creating multiple layers of protection, designing systems so they only fail if all components in a redundancy group fail, not just one. It's like having multiple safety nets.
Okay, safety nets.
For instance, at the server level, instead of one connection, we configure redundant HBAs, host bus adapters, to protect against a single HBA failure to storage. Similarly, NIC teaming is widely used, grouping 2 or more physical network interface cards into a single logical device.
Keeping them up.
Yeah. If one physical NIC fails or its cable is unplugged, network traffic is automatically redirected to another active NIC in the team with no disruption to service. Seamless failover. Moving beyond the server, in the network infrastructure, we see the configuration of redundant switches to ensure no single switch failure brings down connectivity.
2 switches instead of 1.
Right. At the storage layer, implementing multiple storage array ports ensures that even if one port fails, data access continues uninterrupted. Within the storage itself, RAID, redundant array of independent disks, configurations, and hot spares, ensure continuous operation even if an individual disk drive fails.
RAID is pretty standard now, right?
Very much so. And for larger-scale protection against site-wide failures, organizations implement redundant storage arrays at remote sites, synchronously or asynchronously replicating data, so that if the primary data center goes down, the remote site can take over. And at the compute layer, server clustering is a cornerstone. This allows 2 or more servers to access the same shared data volumes, constantly exchanging heartbeats to monitor each other.
Listening to each other.
Basically, yeah. If one server fails, the other can immediately detect it and take over the workload, redirecting users and applications seamlessly. Even more advanced, VM fault tolerance is a virtualization feature that creates a live duplicate VM on a separate physical server, keeping it in lockstep synchronization with the primary VM.
A live copy.
Exactly. If the primary VM fails, the duplicate instantly becomes active, ensuring zero downtime and zero data loss for that specific VM. It's about layers upon layers of protection.
That's a truly robust approach. But all that built-in redundancy, all those alternative paths, don't just magically work, right? You need something intelligent to manage those paths, to direct traffic when a primary path fails, or to balance the load. That's where multipathing software comes in. How does that tie into the strategy?
You hit on a crucial point. Simply configuring multiple physical paths isn't enough. If one path fails, I/O won't automatically reroute unless the system is intelligent enough to recognize and utilize an alternative. This is where multipathing software becomes absolutely essential. It provides the core functionality to recognize and actively use those alternative I/O paths to your data.
So it sees the other roads available.
Precisely. It intelligently manages load balancing by distributing I/Os across all available active paths, maximizing the utilization of your storage infrastructure. And most critically, if a path to a storage device fails due to a cable snag, an HBA failure, or a switch port going down, the multipathing software automatically reroutes the I/O to an alternative, healthy path.
Without missing a beat.
Without any interruption to the application or users, ideally. In modern virtual environments, this capability is often built directly into the hypervisor itself, or it can be provided by third-party software modules that integrate seamlessly. It's the traffic cop that makes all the redundant pathways actually work.
So with this foundational understanding of why we absolutely need to protect data, the terrifying costs of downtime, the constant threat of planned and unplanned outages, and how we make our systems incredibly resilient through these intricate layers of redundancy and intelligent path management. Let's now zero in on one of the most fundamental and universally applied protection strategies. Backup. It's our ultimate safety net. 2. Backup fundamentals, the cornerstone of data protection. Okay, so let's get to the brass tacks. At its core, what exactly is backup, and why do organizations from the smallest startup to the largest enterprise dedicate so much time, money, and complex architecture to it?
At its simplest, a backup is fundamentally an additional copy of production data. It's created and retained for the sole, critical purpose of recovering lost, corrupted, or otherwise unavailable information.
A spare copy, basically. Your digital insurance policy.
That's a great way to put it. Its importance really boils down to 3 core purposes that drive its implementation. First, and often top of mind, is disaster recovery. These copies are specifically used for restoring data at an alternate site when your primary data center or site is incapacitated due to a major disaster.
Big catastrophes.
Right, whether natural or man-made. The entire strategy here is meticulously guided by 2 critical metrics we touched on earlier: RPO, or recovery point objective.
How much data you can afford to lose.
Exactly, how far back in time your recovered data can be. And RTO, or recovery time objective.
How fast you need to get it back.
Right, again. How quickly that recovery must happen for the business to resume operations. The backup allows you to meet these objectives by having a copy elsewhere.
And the second purpose you mentioned, not the big disasters, but
The second, and arguably the most frequent reason backups are performed in day-to-day operations, is for operational recovery. This is about restoring data from routine, often minor, processing losses. Think about the accidental deletion of an important email by an employee.
oh yeah, done that.
We all have. Or a crucial file becoming corrupted during daily operations. Or a user inadvertently overwriting a document. The vast majority, some studies say upwards of 90% of all restore requests in most organizations fall into this category.
90%, wow.
Yeah, it's about quickly getting back that single file or database entry rather than recovering an entire data center. It's the common, everyday data mishap that backups gracefully handle. And finally, the third purpose is archival. While the lines between backup and archiving are blurring, traditional backups are still performed to meet long-term archival requirements,
Keeping stuff for ages, for legal reasons.
typically driven by regulatory compliance mandates or legal discovery needs. For example, many industries require transaction logs, emails, or financial records to be retained for years or even decades. While specialized content address storage, CAS solutions are becoming the primary choice for structured archiving due to their specific features, traditional backup systems are still widely used by smaller and medium businesses for this long-term preservation.
And all of this has to happen within a very specific and often tight time frame that organizations refer to as the backup window. It sounds like a race against the clock.
It absolutely is. The backup window is the defined period during which a source system, be it a server, a database, or an application, is available for performing a data backup with minimal or acceptable disruption to ongoing production operations.
Finding time when it won't mess things up too much.
Exactly. For a 24/7 global business, that window might be extremely small or even non-existent, pushing organizations towards technologies that can perform backups without affecting users. The shrinking backup window, driven by continuous operation demands, is one of the biggest challenges in modern data protection.
When we talk about backup, it's certainly not a one-size-fits-all approach. Organizations strategically combine different types of backups to meet their varied Arporto goals and business needs. Let's delve into the different backup granularities: full, incremental, and cumulative. How do these differ, and what are their distinct pros and cons?
You're right, it's a strategic blend. Organizations meticulously tailor their approach based on their RPO, RTO, and specific business needs for different types of data. Let's break them down, as understanding these is fundamental to efficient backup. First, the full backup. This is exactly what it sounds like. A complete copy of all the data on the production volumes being protected at a specific point in time. Every single bit of data is copied. The whole thing. The pros are clear and compelling. It provides the absolute fastest recovery because you only need one single copy, the full backup itself, to restore your data. It's the simplest recovery process.
Easy restore. Makes sense.
However, the cons are significant. It requires the most storage space on your backup media because you're copying everything, and it naturally takes the longest time to complete the backup operation itself, which can severely impact your backup window.
Takes lots of space and time. Got it.
Next, we have the incremental backup. This method is designed for efficiency during the backup phase. It copies only the data that has changed since the last full or incremental backup, whichever occurred most recently.
Only the changes since the last backup, whatever type that was.
Exactly. So if you did a full backup on Monday, then Tuesday's incremental only copies Tuesday's changes, Wednesday's incremental only copies Wednesday's changes since Tuesday's incremental, and so on. Its main pro is that it's much, much faster to perform because it's only backing up a very small amount of changed data, drastically shortening the backup window. This is great for daily backups.
Quick backups. Nice.
The significant con, however, is that it takes much longer and is more complex to restore. To perform a complete restoration, you need the last full backup plus all subsequent incremental backups in their precise sequential order.
Uh-oh. All of them. In order.
Yep. Imagine our example. If you do a full backup on Monday, and then incremental backups on Tuesday, file 4 changes, Wednesday, file 3 changes, and Thursday, file 5 changes. To restore to Thursday's state, you'd need the Monday full backup, plus Tuesday's incremental, plus Wednesday's, and finally Thursday's.
Wow, that's a lot of pieces.
It is. If one of those incremental tapes or files is missing or corrupted, your entire restore chain breaks. This complexity can severely impact your RTO. Finally, the cumulative or differential backup. This method offers a middle ground between full and incremental. It copies all data that has changed since the last full backup. It always refers back to the most recent full backup.
Okay, so changes since the last full one.
Correct. The pro of this method is that it's significantly faster to restore than an incremental backup because you only need 2 copies. The last full backup plus the latest cumulative backup. This simplifies the recovery process and improves RTO compared to incremental.
Just 2 pieces to restore. Much better.
The con is that each cumulative backup takes longer to perform than an incremental backup because it accumulates all changes since the last full. So a Thursday cumulative backup would be larger than a Thursday incremental because it includes all changes from Tuesday, Wednesday, and Thursday since the Monday full backup.
Ah, so the backups themselves get bigger each day.
They do until the next full. Let's reuse our Monday-Thursday example. Monday is a full backup. On Tuesday, file 4 changes, so the cumulative backup copies file 4. On Wednesday, file 5 also changes, so Wednesday's cumulative backup copies both file 4 and file 5. On Thursday, file 6 changes, so Thursday's cumulative copies files 4, 5, and 6.
Okay, building up.
Right. If you need to restore to Thursday state, you just need the Monday full backup and the single Thursday cumulative backup. Much simpler and faster than incremental restores, but the backup itself grows larger each day until the next full.
That distinction between incremental and cumulative is absolutely key for designing an efficient strategy. It highlights that there's always a trade-off between backup speed and restore speed. Now, let's talk about the actual components and the operational flow involved in a backup. What are the essential pieces of this complex puzzle, and how do they interact during a typical backup operation?
Right. The architecture of a traditional backup system involves several distinct yet interconnected components. The primary players are the backup server, the storage node, the backup client, and the backup device. Understanding their interaction is crucial to seeing how data is protected.
Server, node, client, device.
Okay. The flow generally starts with the backup server. This is the brain of the operation. It manages and initiates the entire backup process based on a predefined schedule, say, every night at 10 p.m. It coordinates all the other components.
The coordinator.
Essentially, yes. It tells the storage node which backup media to prepare, if using tapes, for instance, instructing it to load the appropriate tape, and simultaneously instructs the various backup clients across your network to gather the specific data that needs to be backed up from their respective systems. Once instructed, the backup clients, these are agents or software running on the servers or applications whose data is being protected, then identify and prepare the data for transfer.
The things being backed up.
Correct. They send their data over the network to the assigned storage node. This data could be files, databases, or even entire application volumes. After the data transfer begins, the client also sends some essential backup metadata information like the number of files backed up, their names, timestamps, and permissions to the backup server.
Metadata. Info about the data.
Precisely. This metadata is vital for later cataloging and searching. The storage node acts as the intermediary. It receives the raw client data, organizes it, and then writes it sequentially or randomly, depending on the media, to the designated backup device.
The middleman writing to the storage.
You got it. This device could be a tape library, a disk array, or a virtual tape library. Importantly, as the storage node writes the data, it also sends additional metadata, such as the exact physical or logical location of the data on the backup device and the precise time of the backup back to the backup server. Finally, the backup server integrates all this information. It meticulously updates its backup catalog with all the received metadata. This catalog is arguably the most critical component for recovery.
The master index.
Exactly. It's a detailed, searchable index of all backed up data, its location, and the point in time it was captured. Without an accurate catalog, finding and restoring data becomes incredibly difficult, if not impossible.
So once that data is safely tucked away on the backup media, how does the reverse process, the restore, work when something inevitably goes wrong and you need to get that data back? That's the moment of truth, after all.
You're absolutely right. The restore process is the moment where all that planning and execution proves its worth. A restore operation typically needs to be initiated manually, usually by an administrator or a dedicated backup operator, through the backup software's restore application.
Someone has to kick it off.
Usually, yes. The process begins with the administrator first selecting the specific client for whom the data restore is requested. Crucially, they can also specify which client will receive the restored data.
Oh, doesn't have to be the original.
Not always. It doesn't always have to be the original source server or system, which offers great flexibility for disaster recovery or testing. The administrator then selects the specific data to be restored, whether it's a single file, a directory, or an entire database, and, importantly, the desired point in time for that restoration, which is guided by your RPO requirements.
Picking the version you want back.
Yeah, right. All this selection information, the blueprint for the restore, comes directly from the comprehensive backup catalog, so the restore application communicates with the backup server for this crucial step. Once the selections are made, the backup server then instructs the appropriate storage node to identify and mount the specific backup media, be it a tape, a disk volume, or a virtual tape, onto the backup device. The data is then read from that device and securely sent over the network to the designated client that's awaiting the restored information.
Okay, reads it, sends back.
Pretty much. It's worth noting that while restoring a simple file might be straightforward, database restorations often require additional log files to ensure transactional consistency and integrity.
Extra steps for databases.
Yeah, and that can significantly extend the recovery time objective, often by hours. It's not always a quick button push. One more absolutely crucial point here, often overlooked, is server configuration backup, or SCB.
Server configuration. What's that?
Many organizations focus almost exclusively on backing up application and user data, but SCB is vital for rapid disaster recovery of an entire system. It creates and backs up entire server configuration profiles, that's the operating system, all its settings, installed applications, and server-specific configurations based on user-defined schedules.
So like a blueprint of the whole server.
Exactly. These backed up profiles are absolutely essential because they can be used to quickly reconfigure a recovery server, often even onto dissimilar hardware, in the event of a catastrophic production server failure. This makes entire system recovery much, much faster than manually rebuilding a server from scratch.
This all sounds like an incredibly complex and delicate balancing act. Given all these components, processes, and trade-offs, what are the key considerations that organizations weigh when designing their overall backup and restore strategy? What keeps backup administrators up at night?
You've hit on the essence. It is a significant ongoing balancing act, a careful blend of technology, process, and business objectives. Several factors constantly influence the optimal backup strategy. First and foremost, as we discussed, RPO and RTO are the North Star. They drive everything.
How much data loss? How fast to recover?
Precisely. They dictate the required backup frequency, the type of media used, faster media for lower RTOs, and the restoration granularity. If you need minutes of data loss and minutes of recovery, your strategy will be vastly different from a system that can tolerate hours. Then there's the retention period, which legally or operationally defines how long backup copies must be kept. Some data might be kept for days, others for decades.
How long to keep the copy?
Right. The choice of backup media or target directly impacts recovery time, as we'll discuss. Disk is generally much faster than tape for restores. The granularity we just detailed, full, incremental, or cumulative, is critical for balancing backup window efficiency against restore complexity. The backup window itself is paramount, finding that optimal time to perform backups with minimal disruption to production operations. For 247 global businesses, this is a constant squeeze.
Always shrinking.
Often forcing the adoption of advanced techniques like snapshots or continuous data protection. File size and number also play a subtle but important role. Backing up a few very large files is generally faster and more efficient than backing up the same volume of data composed of millions of tiny files due to metadata processing overhead.
Interesting. Big files are faster than lots of small ones.
Yeah. Generally, yes. Data compression and deduplication are increasingly vital technologies that save significant space on the backup media and, consequently, can help dramatically shorten the backup window by reducing the amount of data that needs to be transferred and stored. We'll get more into dedupe soon. And finally, location is crucial. Modern organizations often have dozens, if not hundreds, of heterogeneous platforms, diverse operating systems, applications, and hardware spread across various physical locations, both locally and remotely.
Different systems everywhere.
Exactly. All of these need to be accounted for in a holistic backup process to ensure transactional and content integrity across the entire distributed enterprise. It's a constant puzzle of balancing speed, cost, compliance, and recovery capability.
That's a comprehensive overview of the what and why of backup in traditional environments. Now that we have the fundamentals down, from why we need to back up to the different types and what goes into the process, let's look at the actual plumbing. How does all this data actually travel during a backup operation? This brings us to backup topologies. 3. Backup topologies. How data travels. So, starting with the simplest setup, what exactly does a direct attach backup look like in practice, and when would an organization typically choose this approach?
In a direct attached backup scenario, the setup is quite straightforward and localized. The storage node, which acts as the data mover, is actually configured directly on the backup client itself.
The mover is on the client.
Yep. And the backup device, such as a tape drive or a dedicated disk, is physically attached locally to that specific client. So the server being backed up essentially has its own dedicated backup hardware.
Its own little backup system.
Pretty much. During the backup, only the metadata, the information about the data being backed up, like file names and locations, not the actual data content, is sent to the backup server via the local area network, LAN. The primary benefit here is that it completely frees the LAN from backup traffic, as the actual data transfer happens directly between the client and its locally attached device.
Keeps network clear.
Exactly. This makes it a very efficient solution for isolated systems or small-scale environments where only one or a few servers need dedicated backup. However, as an environment grows, it quickly becomes unwieldy and costly due to the lack of centralized management and the inability to share backup devices efficiently among multiple servers. Each server needs its own hardware.
Doesn't scale well.
Not really, no.
Right, so that rapidly becomes inefficient for larger organizations. For scalability and sharing resources, you quickly run into the need for more sophisticated solutions. That's where network-based topologies come in. Let's start with the most common one, LAN-based backup. How does data travel in this setup, and what are its main implications?
In a LAN-based backup, all the primary components, the backup clients, your servers, the backup server, the brain, the storage node, the data mover, and the backup device, where data lands, are all connected to the same local area network.
Everything on the main network.
Correct. This means that when a backup job kicks off, the actual data to be backed up is transferred from the backup client, which is the source, to the storage node, and then onto the backup device, all directly over the LAN. While it's relatively simple to set up due to its reliance on existing network infrastructure, a major drawback is that this constant data transfer can significantly affect network performance.
Clogs up the network.
It definitely can, especially during a large simultaneous backup jobs or if the LAN is already heavily utilized for production traffic. It creates a bottleneck. To mitigate this impact, larger organizations often configure separate, dedicated networks specifically for backup traffic, creating an out-of-band backup network.
A separate highway for backups.
Kind of, yeah. Or they might deploy multiple dedicated storage nodes for certain application servers to distribute and offload that backup traffic from the main production network. But without such measures, it can definitely slow down your business operations.
So LAN-based can definitely create bottlenecks, if not carefully managed. What's the alternative that helps alleviate that network strain, especially for critical data moving between servers and storage? That's the SAN-based or LAN-free backup.
SAN-based backup is often the preferred solution in enterprise environments, particularly when multiple clients need to share high-speed backup devices and you want to minimize impact on your primary network.
Using the storage area network, the SAN.
Exactly. In this topology, both the backup device, which is usually a dedicated disk array or a virtual tape library, and the backup clients are physically attached to the storage area network, or SAN. This means that the vast majority of the backup data traffic is restricted entirely to the SAN, a high-speed dedicated network for storage.
So backup data stays on the SAN.
Mostly, yes. Only the insignificant volume of backup metadata, the index information, is transported over the traditional LAN to the backup server. Because the heavy data lifting is happening on the SAN, the LAN performance is not degraded during the backup process,
Keeping the main network free.
allowing your users and applications to continue operating without interruption. This configuration also greatly facilitates the use of high-performance disk arrays directly attached to the SAN as primary backup devices, which has become increasingly common with the availability of high-capacity, low-cost disk storage. It's a significant step up in efficiency and performance.
And what about a scenario where an organization might need a bit of both, perhaps for different applications, locations, or types of data?
That's where a mixed topology comes into play. It's very common in large, heterogeneous enterprise environments. Organizations often implement a pragmatic combination of LAN-based and SAN-based topologies to optimize for various factors.
A mix-and-match approach.
Exactly. This approach can be driven by cost considerations. Maybe some less critical data can still go over the LAN. It could be dictated by the physical location of servers. Some may be in remote branches with only LAN connectivity. It might be a desire to reduce administrative overhead for certain simpler systems, or to meet very specific performance requirements for different mission-critical applications. It allows for tremendous flexibility and optimization across diverse operational environments, leveraging the strengths of each topology where it makes the most sense.
Moving on to a specific environment, Network-attached storage, or NAS, presents its own unique challenges for backup. This is because NAS heads often run proprietary operating systems and file systems, and they support multiple protocols like CIFS and NFS. How is backup typically handled in a NAS environment, and what are the main approaches?
You're right. NAS environments introduce specific complexities due to their unique architecture. There are typically three main ways to implement backups for NAS, each with its own trade-offs: the application server-based method, serverless backup, and the industry standard Network Data Management Protocol, or NDMP.
Okay, 3 ways for NAS. Let's start with application server-based.
Right. In this scenario, the NAS head retrieves the data from its underlying storage array over the network. This data is then transferred to a backup client running on a separate application server. That backup client then processes the data and sends it over the network to a storage node, which finally writes it to the backup device.
So NAS to app server to storage node.
Hmm.
Lots of hops.
Exactly. The major downside here is significant. This method can lead to overloading both your production network with backup data and consume substantial processing and memory resources on the application server itself to move that data,
Slowing down the app server.
potentially impacting the performance of the very applications it's supposed to be protecting. It's generally less efficient. The second approach, a significant improvement, is serverless backup for NAS. In this scenario, instead of routing through an application server, the network share from the NAS head is mounted directly on the storage node itself.
Mounts the NAS share right on the storage node.
Yep. The storage node, which in this configuration also acts as a backup client, reads the data directly from the NAS head and writes it directly to the backup device. This setup effectively bypasses the application server entirely.
Takes the app server out of the loop.
Exactly. The key benefits are clear. It avoids overloading the network during the backup process by streamlining the data path, and it completely eliminates the need to use CPU and memory resources on the application server for backup operations. You remove one significant network hop and free up valuable application server resources.
And then there's NDMP, or Network Data Management Protocol, which sounds like a specialized, purpose-built solution for NAS environments. What makes it different, and why is it so widely adopted?
NDMP, or Network Data Management Protocol, is indeed an industry standard TCP/IP-based protocol designed specifically to optimize backup and recovery operations in NAS environments.
Built just for NAS backup.
Pretty much. Its core purpose is to facilitate direct communication among various elements in the backup environment, namely the NAS head itself, the backup devices, and the backup server, specifically for efficient data transfer. Its flexibility is a huge advantage. Data doesn't need to be transported through an application server or even the main production LAN, which significantly reduces the load on those servers and dramatically improves backup speed.
Direct connection between NAS and backup device.
Essentially, yes. NDMP optimizes backup and restore by leveraging high-speed connections directly between the backup devices and the NAS head. So the vast backup data is sent directly from the NAS head to the backup device, while only the lightweight metadata and control information are sent over the network to the backup server. Within the NDMP framework, we have two common implementations that address different needs: NDMP 2-way and NDMP 3-way.
2-way and 3-way. Okay.
In NDMP 2-way, the goal is to minimize network data movement entirely by isolating it. The data flows directly from the NAS head to a backup device that is physically attached locally to that specific NAS head.
Device attached right to the NAS.
Correct. Only metadata is transported over the network. While this minimizes network traffic to an absolute minimum, a drawback is that the backup device is dedicated to that specific NAS device, making centralized management of all backup devices across multiple NAS units more challenging.
Harder to share the backup device.
Right. NDMP 3-way is designed for larger, more complex environments where backup devices need to be shared efficiently among multiple NAS heads. To prevent backup data from traversing the production LAN, a separate private backup network is typically established between all the NAS heads and the specific NAS head that's connected to the shared backup device.
A private network just for NAS backup traffic.
Usually, yes. Data flows from a source NAS head over this private network to the NAS head connected to the backup device and then to the device. Metadata and NDMP control data still cross the public network. This is particularly useful when you need to centralize and share high-capacity backup devices among several NAS heads, allowing one NAS head to control a device and share it by receiving backup data through the NDMP protocol from other NAS heads. It's about optimizing for shared resources in a large-scale NAS environment.
That's a truly comprehensive look at how data travels during backup. addressing everything from the simplest direct attachment to complex NAS environments, showing the different paths the data takes. Now, for the data itself, once it's collected and processed, where does it all go? Let's talk about the destinations, the physical and virtual locations where our digital backups reside. Backup targets. 4. Backup targets. Where data resides. For a long time, for decades really, when you thought backup, the first thing that probably came to mind was tape. So let's start there. What are the key characteristics, the pros, and perhaps more importantly, the significant cons of physical tapes as a backup target in today's digital landscape?
You're right. Physical tapes have been the workhorse of backup for a very long time, primarily due to their low per gigabyte cost and high capacity.
Cheap storage.
Relatively cheap, yes, making them an appealing solution for long-term archival or offsite storage. Tape drives are fundamentally sequential access devices, meaning data is written and read linearly from beginning to end, much like an old audio cassette. You have to spool through to find what you need.
Like fast-forwarding a cassette. Slow.
Exactly. While their low cost is a draw, especially for data that needs to be stored for extended periods and rarely accessed, they come with significant drawbacks in a world demanding instant access and rapid recovery. The sequential access nature of tapes inherently slows down both backup and, critically, recovery operations. Unlike disk drives, where the read-write head never physically touches the platter, tape drive heads do make contact with the tape surface.
Wearing down the tape.
Right. This means tapes can degrade or wear out after repeated use, leading to potential data corruption or loss over time. There's also considerable storage and retrieval overhead associated with managing physical tape media, labeling, inventorying, loading tapes into drives, and the physical transport to offsite locations.
A lot of manual work.
A lot. For enterprise-class data centers today, tapes are no longer the preferred choice as a primary backup destination for operational recovery, largely due to the widespread availability of high-performance, low-cost disk drives that offer random access. Tapes require a controlled environment-specific temperature and humidity for long-term preservation and are susceptible to environmental wear and tear.
Sensitive things.
And furthermore, the physical transportation of tapes to off-site locations adds significant management overhead and crucially increases the possibility of loss or theft of sensitive data during transit.
Risky moving them around.
Definitely. And finally, there's the infamous shoe shining effect, which occurs when the tape drive repeatedly starts and stops or moves back and forth to match an inconsistent data stream.
Shoe shining. Like polishing shoes.
Kind of looks like it. This constant shuttling causes further physical degradation of the tape and significantly slows down backup and restore performance. While still used for very deep, cold archives, tapes are generally not for active operational recovery.
So, given those limitations of tapes, especially the sequential access and management overhead, it's not surprising that disk drives have emerged as the dominant, low-cost, and high-performance backup medium in modern IT. What advantages do disks offer that have made them the go-to solution?
Disk drives are indeed the most ubiquitous and popular storage medium in modern computing, and for good reason. Unlike tapes, disks provide rapid random access to data locations.
Jump straight to the data.
Exactly. This is a game changer. It means data can be written or retrieved almost instantaneously from any point on the disk, making them incredibly efficient for supporting a large number of simultaneous backup streams or enabling rapid, granular recovery operations. They also offer massive capacities, continuing to grow in density at a phenomenal rate, and when configured in disk storage arrays, they provide not just increased capacity, but also enhanced performance through striping and caching.
Faster and bigger.
Right. This fundamental difference in access random versus sequential makes disks inherently superior for faster backup and, critically, vastly faster recovery operations, which is often the primary driver for modern businesses facing tight RTOs. Their reliability is also very high, and management is entirely electronic, eliminating the physical overhead of tapes.
Now here's where it gets really interesting, showing how innovation bridges old and new. What if you want to harness the incredible speed and reliability benefits of disk, but you're stuck with legacy backup software that was specifically designed for managing tape libraries? This is where the Virtual Tape Library, or VTL, comes in, cleverly bridging that gap. How does it work its magic?
The Virtual Tape Library, VTL, is a truly clever and pragmatic solution that perfectly illustrates how innovation can leverage new technology while preserving existing investments. Essentially, a VTL uses standard disk drives as its underlying storage media, but these disk drives are emulated and presented as physical tape drives and tape libraries to your existing backup software.
So it pretends to be tape, but it's really disk.
Exactly. The magic is in the emulation. The key benefit here is immense. It requires absolutely no changes to your legacy backup software. You preserve your significant investment in existing infrastructure, processes, and administrator training.
Doesn't break the old software.
Right. Your backup application simply sees a VTL as a traditional tape library, but underneath, it's all spinning disk. Compared to physical tapes, VTLs offer much better single-stream performance during backup and restoration, significantly higher reliability because there are no physical tapes to wear out, and the inherent random access characteristics of disks,
Faster, more reliable.
which translates directly to dramatically faster backup and recovery operations because all your tapes are always online and instantly accessible on disk. With a VTL, you completely eliminate the need for physical tape drive maintenance, like periodic cleaning, calibration, or replacing worn-out heads. Installation and administration are typically much easier because VTLs often come pre-configured by the manufacturer, ready to integrate into your existing backup environment.
Easier to manage.
Much easier. All the traditional tape components, the virtual tapes, virtual tape drives, and even the virtual robot arm mounts, are completely virtualized. The system uses vast amounts of disk as its media, and clever emulation software maps these virtual tapes to underlying logical unit numbers, or all LUNs.
Fancy term for blocks of disk space.
Essentially, yes. LUNs are blocks of storage from a disk array presented to the VTL. Crucially, a VTL is not constrained by the sequential access limitations or the shoe shining effect that plague physical tapes. When a backup process starts, a robot mount is virtually performed, but unlike physical libraries where you wait for an arm to move, it's instantaneous.
Instant mount.
The virtual tape is immediately ready for data. Similarly, a rewind command after an operation is also instantaneous, and the virtual tape is unmounted and returned to a virtual slot just as quickly. Restore operations, while emulating tape behavior, are nearly instantaneous due to the underlying random access disk technology. It truly provides the best of both worlds: disk performance with tape compatibility.
That's a massive leap in efficiency and eliminates so many headaches associated with physical media. Whether it's tape, disk, or VTL, one major challenge in backup is the sheer volume of redundant data that gets copied over and over. This leads us perfectly into data deduplication, cutting the clutter. It's arguably one of the most impactful innovations in backup in the last 2 decades. Data deduplication, cutting the clutter. So what exactly is the problem that data deduplication aims to solve, and what is this technology at its heart? Why is it so revolutionary for modern data protection?
The problem is immense and growing. In traditional backup solutions, there's no inherent capability to prevent the same exact data from being backed up multiple times. Imagine you have 100 employee laptops all running the same operating system, the same set of productivity software, and maybe many of the same corporate documents.
Lots of identical files.
Exactly. When you back them all up individually, you're copying terabytes of identical data over and over again. With the explosion of information and the demand for 247 application availability, backup windows are shrinking rapidly, making it impossible to copy all that redundant data. This repeated copying of identical data consumes an outrageous amount of valuable resources, precious storage space on your backup devices, and critically, immense network bandwidth. And it inflates your backup window to an unacceptable degree.
Wasting space, time, and network.
Totally. Data deduplication is the elegant solution to this very expensive problem. It's the process of intelligently identifying and eliminating redundant data within a dataset.
Finding the duplicates and getting rid of them.
Sort of. Here's the magic. Instead of storing multiple identical copies of a file, a block, or even a sub-block of data, deduplication works by comparing incoming data against data already stored. When a duplicate piece of data is detected, the redundant copy is discarded, and instead, only a very small pointer or reference is created.
A pointer, like a shortcut.
Precisely. This pointer simply refers to the single existing copy of that data that has already been backed up. It's like saying, I don't need to save this entire document again. I'll just put a note here saying it's the same as document A. The benefits are truly transformative. It dramatically reduces the storage requirements for backup data, often by ratios of 10.1, 20.1, or even higher, depending on the data
Look at
type.
huge space saving.
Massive. This, in turn, helps to shorten the backup window because less data needs to be written. It removes substantial burden from the network by not transmitting redundant data. Ultimately, this allows organizations to store significantly more backups on faster disk media and retain that data on disk for a much longer time, improving both RPO and RTO.
So it's about making our backup infrastructure vastly more efficient, saving space, time, and network bandwidth. But how is deduplication actually performed? Are there different methods or implementations that organizations can choose from?
Yes, there are two primary approaches based on where the deduplication process occurs in the data path: source-based and target-based. Each has distinct advantages and trade-offs.
Source or target? Okay.
First, source-based deduplication, often referred to as client-side deduplication. This is perhaps the most efficient method in terms of network usage. It works by eliminating redundant data at the source, that is, on the backup client server itself, before that data is even transmitted over the network to the backup device.
Dedupe before sending it over the
There,
network.
exactly. The pros are incredibly compelling. It dramatically reduces the amount of backup data that needs to be sent across the network, leading to a much shorter backup window and requiring significantly less network bandwidth. This also results in a substantial reduction in the overall capacity needed to store the backup images on the target device. It's ideal for environments with constrained networks, like remote offices.
Great for slow networks?
However, there are cons. This method increases the processing overhead on the backup client itself, as the client's CPU and memory are used to perform the deduplication calculations.
It's the performance of the client server.
It can potentially impact the performance of the client server and the applications running on it during the backup window. It might also require specific backup software changes or agents to support this capability.
So that offloads the network but puts the burden on the source server. What's the alternative to that client-side approach where the processing is shifted elsewhere?
The alternative is target-based deduplication, where the deduplication process occurs directly at the backup device itself, effectively offloading the CPU and memory burden from the backup clients.
Dedu happens at the storage end.
Right. Within target-based deduplication, we have two further methods, depending on when the deduplication happens. Inline deduplication performs the deduplication before the data is actually stored on the backup device. As data arrives at the target, it's immediately analyzed and deduplicated.
Dedupe as it arrives.
Its main pro is that it immediately reduces the storage capacity needed for the backup, as only unique data blocks are ever written to disk. The con is that it introduces a slight overhead in terms of the time required to identify and remove duplication during the backup process. This can extend the backup window slightly, making it best suited for environments with slightly larger backup windows or less strict RTOs.
A bit slower during backup.
Then there's post-process deduplication. With this method, the backup data is stored on the backup device first in its raw, undeduplicated form. Deduplication is then performed later, typically during off-peak hours or at a scheduled time as a background task.
Store first, dedupe later.
The key pro here is that it's suitable for situations with tighter backup windows because the initial storage operation is incredibly fast. It's just writing raw data. The con is that it requires more initial storage capacity to temporarily hold the backup images before they are deduplicated. You need enough buffer space to hold the undeduplicated data until the post-process task can run.
Need extra space temporarily.
Exactly. For target-based methods in general, all the backup data must be transferred over the network to the backup device before deduplication occurs, unless it's source-based. This means it generally increases network bandwidth requirements compared to source-based deduplication.
Still sends all the data over the network first.
Right. But a significant advantage is that target-based deduplication typically doesn't require any changes to existing backup software or agents on the client side, making it easier to implement in heterogeneous environments.
So, regardless of whether it happens at the source or the target, the core benefits of deduplication remain the same. Reducing the backup window, and especially with source-based, drastically reducing the network bandwidth required. This sounds like it could be a complete game changer for remote or branch offices, which often have limited IT staff and network connectivity.
It absolutely is, and it has indeed been a massive game changer for remote office backup. Many businesses have remote or branch offices with their own local IT infrastructure, generating significant amounts of data. Traditionally, backing up this critical data was often a cumbersome manual process using tapes, which then had to be physically shipped off-site.
Shipping tapes back and forth.
Yeah.
Nightmare.
Total nightmare. This came with numerous challenges. A lack of skilled on-site technical resources, the inherent risk of loss or theft during transit, and the prohibitive cost and time involved in sending huge volumes of data over a wide area network WAN back to a central data center. Disk-based backup solutions combined with source-based deduplication specifically eliminate these challenges for remote offices. By dramatically reducing the amount of data that actually needs to be transmitted, deduplication drastically reduces the network bandwidth needed.
Makes WAN backups feasible.
Exactly. This allows remote office data to be backed up efficiently over existing WAN links, often during business hours, without impacting other network traffic. This means organizations can centrally manage and automate remote office backups, eliminating the need for manual tape handling and significantly reducing the required backup window. It transforms a complex, risky, and costly operation into a streamlined, automated, and secure process.
Fascinating stuff. We've talked extensively about the why and how of backup in traditional physical environments, from the foundational need to the various types, architectures, and the incredible efficiency gains from deduplication. Now, for the main event, the digital landscape has been fundamentally reshaped by virtualization. So how do all these backup concepts, strategies, and technologies change or adapt or even get redefined when we move into the incredibly dense and dynamic world of virtualization? This is where it gets really interesting, showing how a foundational shift in infrastructure impacts everything upstream. This is the core of today's lesson, right?
Yeah.
Backup in virtualized environments. Backup in virtualized environments, the game changer.
Exactly. This is the heart of it.
So first things first, as we step into this virtualized world, is backing up VM data truly as crucial as backing up physical servers? Or is there a perception out there that virtualization somehow makes data magically safe or inherently redundant?
It's an excellent question and a crucial one. There can sometimes be a misconception that because data in a virtual machine is abstracted or can be easily moved, it's somehow less vulnerable. That is absolutely not the case.
Virtual doesn't mean invincible.
Not at all. It is absolutely imperative to back up virtual machine data, and that includes the operating system, all application data, and critical configuration files, just as diligently as you would physical servers. VMs are still susceptible to data loss or corruption due to human errors, software bugs, or underlying hardware failures. Just because it's virtual doesn't mean it's invulnerable to accidental deletion, file corruption, or even a ransomware attack. In fact, due to the increased density of workloads and the sheer number of VMs in modern data centers, backup optimization methods are even more necessary here. And this is precisely where data deduplication, which we just discussed, truly shines and becomes incredibly effective.
Deduplicate works well with VMs.
Exceptionally well. Virtualized environments are a prime target for deduplication because you often have multiple VMs running remarkably similar configurations. Think about it. Multiple VMs running the exact same version of Windows Server or a dozen instances of the same application stack.
Yeah, lots of identical OS files and stuff.
Exactly. This creates an enormous amount of redundant data across those VMs' identical OS files, application binaries, and patches. Deduplication can efficiently eliminate these common data blocks, leading to massive storage savings for your VM backups. The deduplication types and methods we just discussed, source-based and target-based, inline and post-process, are used in a virtualized environment in the same way as they are in a physical environment, but with often higher efficiency gains due to the inherent similarities across VMs.
Okay, so the imperative for backup is clear, and deduplication is an incredibly powerful tool in this virtualized context. Let's look at how traditional backup approaches first adapted when virtualization became widespread. If you were using a traditional backup solution, where would you typically install a backup agent in a virtualized environment? What were the options and what were their limitations?
Right. In the early days of widespread virtualization, traditional backup approaches adapted in two main ways for agent deployment. The first, and most straightforward, was to install a backup agent directly on the virtual machine VM itself.
Agent inside the VM, just like a physical server.
Exactly. From the perspective of the backup agent, the VM simply appears as a physical server. The agent operates within the guest operating system of the VM, just like it would on a physical machine, and backs up the VM's data to the backup device. However, the significant drawback of this method is that the agent installed inside the VM only sees the files and data within that guest OS. It does not capture the essential VM files themselves.
Like the VM's configuration files.
Right. Things like the virtual BIOS file, the VM swap file, critical log files, or crucially, the virtual machine's configuration files, like the .vmx file in VMware. This means that for a complete VM restore after a catastrophic event, a user would first need to manually recreate the virtual machine infrastructure, assigning virtual CPUs, memory, network adapters, and creating the virtual disk files, and then restore the data onto that newly created empty VM.
Ugh, sounds painful. Rebuild the VM first, then restore data.
It's a complex, multi-step, and time-consuming recovery process, increasing your RTO significantly. The second traditional approach aimed to simplify agent management, installing the backup agent directly on the hypervisor itself, the software layer that manages all the VMs.
Agent on the host server, the hypervisor.
Correct. In this model, the VMs don't appear as individual servers to the agent, but rather as a set of large files residing on the hypervisor's underlying file system or storage. The pros of this approach are notable. It's relatively simpler from a management perspective because you only need to manage a single agent on the hypervisor, rather than deploying and maintaining agents on every individual VM, which could be hundreds.
One agent instead of hundreds. Easier management.
Much easier. Crucially, because the hypervisor agent sees the entire VM as a collection of files, including the virtual disks and configuration files, it can capture all those essential VM files, making for a more complete and much easier full VM restore. You could potentially restore the entire VM as a single entity.
So it gets the whole VM package, better restore.
However, a significant con is that this method can cause high CPU utilization on the backed up server, the hypervisor itself, during backup operations.
Slows down the hypervisor, which slows down all the VMs running on it.
Potentially, yes. This means that the backup operations should ideally be performed when hypervisor resources are idle or during periods of low activity on the network, which is rarely achievable in a 247 production environment. In environments with a large number of VMs, careful resource allocation is required to manage the backup load on the hypervisor, potentially impacting the performance of the very VMs it's hosting. It becomes a bottleneck for the entire virtual environment.
While those traditional agent-based methods certainly work to a degree, they clearly came with performance trade-offs and operational complexities, particularly for the hypervisor. But the true power and elegance of virtualization for backup often comes with a fundamentally different and far more modern approach: image-based backup. Tell us about this game-changing solution and why it's become the gold standard.
Image-based backup is indeed a paradigm shift, a truly game-changing solution, because it operates directly at the hypervisor level and redefines how we think about data protection in virtual environments.
Working at the hypervisor level, okay.
Instead of backing up files within a VM, or even the VM's files from the hypervisor, it essentially takes a snapshot of the entire VM as a complete self-contained unit. It's like pressing pause on the VM and copying its entire digital footprint.
A snapshot of the whole VM.
Exactly. Here's how it works and why it's so powerful. The process creates a complete, consistent copy of the guest operating system and all its associated data. Think of it as a point-in-time snapshot of the VM's virtual disk files, its memory state, and all application configurations at that precise moment. This complete, consistent backup is then saved as a single image file.
One big file for the whole VM.
Right. Crucially, this large image file is then mounted on a separate, dedicated proxy server, which acts as the backup client. The backup software then backs up these image files normally from the proxy server, effectively treating the entire VM image as a large, static file to be backed up to your target media.
So the hard work happens on a separate proxy server.
Precisely. The key benefit here is enormous. It dramatically offloads the backup processing from the hypervisor itself to that dedicated proxy server. This significantly reduces the impact on the VMs running directly on the hypervisor, allowing them to continue their production workloads with minimal disruption, even during backup operations.
Solve the hypervisor slowdown problem.
Exactly. It addresses the CPU utilization problem of the hypervisor agent approach. And for recovery, it enables the incredibly quick restoration of an entire VM from that single image file. Instead of having to rebuild a VM and then restore data piecemeal, you can bring the entire VMOS applications and data back online quickly and consistently, essentially as it was at the time of the snapshot. It transforms a potentially multi-step, complex restoration process into a much faster, unified operation.
That's the real aha moment
Yeah.
right there. The abstraction that virtualization provides allows for a fundamentally different and often vastly more efficient approach to backup. You're not just backing up files, you're backing up the entire encapsulated self-contained virtual machine.
Yeah.
This must have a huge impact on recovery time objectives for full VM failures.
Precisely. By capturing the entire VM as a coherent single image, including its operating system, installed applications, and all configurations, image-based backup allows for incredibly fast response times when you need to recover from a VM failure. Instead of a piecemeal, lengthy restoration, you can bring the entire VM back online quickly, often within minutes, significantly improving recovery time objectives for the business. This directly translates to less downtime and less financial impact. However, it's also important to be aware of a couple of considerations related to VM snapshot technology, even with image-based backups. While immensely powerful, this approach generally does not support data replication if a virtual machine accesses its data by using raw disks.
Raw disks,
Yeah.
like direct access to storage.
Yeah, rather than the standard virtual disk files like VMDKs or VHDs, raw disks, or raw device mappings, RDMs, are direct connections to physical storage volumes that bypass the hypervisor's file system, which can make them tricky for hypervisor-level snapshotting and replication. Also, while the bulk of the processing is offloaded to the proxy server, the initial act of using the hypervisor to perform the actual snapshot of a running VM can still temporarily increase the load on the hypervisor's compute resources and impact compute performance for a brief moment.
A brief hit on the hypervisor when the snapshot happens.
Potentially, yes. It's a trade-off, but the benefits of rapid, complete VM recovery and reduced operational burden generally far outweigh these specific considerations for most virtualized workloads. It's an incredibly powerful tool when used appropriately.
So we've explored how we protect data that's actively being used, accessed, and changed, our live production data. But what about data that isn't changing much, or perhaps at all, but still needs to be kept for a very long time, sometimes decades? This leads us to data archiving, long-term data preservation. It's a completely different mindset to traditional backup, moving beyond just operational recovery. 7. Data archiving, long-term data preservation. Let's start by defining what we mean by fixed content, because that's the specific type of data that archiving solutions are designed for, and how that relates to the concept of a data archive.
Okay, fixed content refers to digital information that, while actively created, accessed, and perhaps even changed initially, reaches a point where it becomes less likely to be modified. As it ages, it eventually becomes fixed, meaning its content won't change, but it critically still needs to be accessed by applications and users, often for legal, regulatory, or historical business purposes.
Data that's set in stone, but you still need to look at sometimes.
Exactly. Think about medical x-rays or patient records. Once an x-ray is taken, its content is fixed, but it might be accessed repeatedly over a patient's lifetime. Other examples include detailed CAD/CAM designs that define a product, financial documents like check images or loan contracts, and even raw surveillance video footage. This category of data is absolutely exploding, growing incredibly rapidly, often over 90% annually in many organizations.
Well, growing fast.
A data archive is then defined as a dedicated, managed repository specifically for this fixed content. Its fundamental purpose is to enable secure, long-term retention of data, often for years or even decades, to meet stringent regulatory compliance requirements, address potential legal discovery needs, and increasingly to support new business intelligence strategies that derive value from analyzing historical information.
Keeping old data safe and accessible for the long haul.
Right. Archives can be implemented with varying degrees of accessibility. An online archive means the storage device is directly connected and immediately accessible, usually in seconds.
Quick access.
A nearline archive implies the device is connected, but the media or device where the data is stored needs to be mounted or loaded for access, which might take minutes.
Takes a little longer.
And an offline archive refers to a device or media that's not ready to use at all, requiring significant manual intervention like retrieving a tape from offsite storage to connect, mount, or load before data can be accessed, often taking hours or days.
Really slow manual process.
Exactly. The modern goal for fixed content is often long-term preservation with simultaneous fast online access, which poses a significant challenge for traditional methods.
Speaking of traditional methods, archiving solutions like optical media, worm disks, or even tapes have been around for a while, but they always seem to come with significant headaches. What were the inherent shortcomings of these traditional archiving solutions for today's data volumes and compliance demands?
While inexpensive on a per gigabyte basis, traditional optical media, particularly write-once-read, many worm disks, and physical tapes presented significant drawbacks for modern archiving needs, especially for enterprises. They often involved high operational, management, and maintenance overheads, requiring manual handling, environmental controls, and constant attention.
Lots of babysitting.
Pretty much. These solutions were also not optimized to recognize content, meaning if the same document was archived by 3 different departments, 3 copies would be stored, wasting valuable space.
Storing duplicates.
Wasteful.
Very. There were often substantial additional costs associated with offsite storage and the labor-intensive media management. Critically, tapes and optical media are susceptible to physical wear and tear over time.
Media degrading again.
And frequent technological changes meant an ongoing overhead of converting media into new formats every few years to ensure continued access and retrieval, a process known as data migration or refreshing.
Constantly having to copy it to new tapes or disks.
Yeah, a huge pain. Furthermore, with ever stricter government and industry regulations demanding protection against unauthorized destruction, alteration, and ensuring the absolute authenticity of archived information, these traditional solutions proved increasingly inadequate for ensuring the true integrity and auditability of archived information over the long term.
Didn't meet modern compliance rules.
They lacked the built-in features for non-repudiation or tamper-proofing required by modern compliance. This is precisely why Content Address Storage, or CAS, has emerged as a revolutionary disk-based alternative that specifically addresses all these issues.
CAS, Content Address Storage.
Right. CAS is purpose-built for the secure online storage and rapid retrieval of fixed content. It overcomes many of the shortcomings of traditional methods by assigning a globally unique content address to each object stored. This address is derived from the object's binary representation, which effectively means if the content changes even by 1 bit, its address changes.
So the address proves the content hasn't changed.
Exactly. It intrinsically guarantees content authenticity and integrity. The data hasn't been tampered with. CAS also offers location independence, meaning the physical location of the data within the system is irrelevant to its access, simplifying management. It provides single instance storage, SIS, preventing duplicate content from being stored, leading to massive space savings.
Built into dupe for archive.
Essentially, yes, it can automatically enforce retention policies for compliance, includes self-diagnosis and repair capabilities to ensure data availability over decades, and maintains comprehensive, immutable audit trails.
All the stuff needed for compliance.
All of which are absolutely crucial for compliance and long-term preservation. It's an active, intelligent archive.
So CAS provides a truly robust and intelligent foundation for long-term data preservation. What does a typical archiving solution architecture look like in a modern enterprise? And can you give us some truly powerful real-world use cases where archiving makes a massive difference?
Okay. A modern archiving solution architecture typically consists of 3 key interconnected components designed for seamless operation and compliance. First, the archiving agent.
An agent, again, like with backup.
Similar idea, yeah. This is software installed on the application server, whether it's an email server, a file server, or a custom application server. Its primary job is to scan data based on intelligent policies defined on the archiving server, identifying what content is suitable for archiving. For example, files older than 5 years, emails from departed employees, specific document types. Once data is identified and confirmed as fixed content, the agent sends that data securely to the archiving server. And critically, the original data on the primary application server is then replaced with a small stub file.
A stub file, like a placeholder.
Exactly. This stub file, containing the unique content address of the archived data, saves significant space on expensive primary storage. When a user or application tries to access the original file, the stub transparently retrieves it from the archive storage device.
Seamless access for the user.
That's the goal. Second, the archiving server. This is software running on a central host that acts as the brain of the archiving system. It allows administrators to meticulously configure and enforce the policies for archiving data.
Setting the rules for what gets archived.
Right. These policies can be incredibly granular based on criteria like file size, type, age, creation, modification, or last access time, or even content metadata. The archiving server receives the data from the archiving agents across the network, processes it, performs operations like content addressing and single instance storage, and then sends it efficiently to the dedicated archive storage device. And third, the archive storage device itself. This is the ultimate destination where the fixed content is persistently and securely stored for the long term. This is typically a content address storage, CAS system, or a similar highly scalable, resilient, and intelligent disk-based solution designed for immutable storage and rapid retrieval.
The secure vault for the archive data.
You got it. Now, for some powerful transformative use cases that highlight the impact of archiving, Email archiving is a prime example. System administrators typically configure small mailbox quotas for users due to the immense management complexity, high primary storage costs, and potential performance degradation that comes with very large mailboxes.
Yeah, always running out of mailbox space.
Exactly. This often forces users to delete older emails, even if they're legally required or business critical. An email archiving solution fundamentally changes this. It automatically moves emails identified for archive from expensive primary storage to more cost-effective archive storage based on predefined policies. For instance, archive emails older than 90 days.
Moves old emails off the main server.
Right. The significantly saves space on primary storage, allows users virtually unlimited mailbox space, as older emails are still accessible transparently via stubs or search interfaces, and crucially helps organizations meet stringent regulatory and legal requirements for long-term email retention, preventing data sprawl and ensuring compliance. Another excellent use case is in a file-sharing environment, like shared network drives or corporate file shares. Users often store a massive number of files in these locations, many of which are old, rarely accessed, or even duplicates.
Shared drives get messy fast.
Tell me about it. Administrators might impose quotas, forcing users to delete files they may still need, or leading to constant requests for increased, costly primary storage. A file archiving solution addresses this by actively scanning and archiving files based on policies like age, size, or last access date. This considerably reduces primary storage requirements, reclaiming valuable space, and enables users to retain files in the archive for much longer periods without impacting the performance or cost of active primary storage. Files can be moved non-disruptively and retrieved transparently, making the archive feel like an extension of the primary storage.
Cleans up shared drives and saves money. Nice. We've covered a tremendous amount of ground today, from the fundamental, compelling need for data protection to the intricate details of backing up virtualized environments, and finally, the critical role of archiving fixed content for long-term preservation and compliance. This deep dive has truly spanned the landscape of modern data preservation, from milliseconds of recovery to decades of retention. Outro. So, to recap our truly extensive journey, we started by solidifying our understanding of the essential nature of business continuity and information availability in our data-rich 21st century world, meticulously examining the severe consequences of downtime and the vital metrics used to measure it, like MTBF and MTTR. We then explored the critical need to mitigate those elusive single points of failure through robust defense-in-depth strategies and the clever role of multipathing software that makes all that redundancy actually work.
From there, we delved deeply into the cornerstone of data protection backup fundamentals, breaking down the three core purposes of backup: disaster recovery, operational recovery, and archive. We looked at the nuances of different granularities like full, incremental, and cumulative, and the intricate architectural components, server, client, node, device, that make it all work seamlessly. We then followed the data's complex journey through various backup topologies, from the simplicity of direct attached to the complexities of network-based, LAN and SAN, and specialized NAS environments using NDMP. Before examining the fascinating evolution of backup targets, from the limitations of physical tapes to the incredible advantages of disks and the ingenious virtual tape libraries.
And to make all this vastly more efficient, we thoroughly dissected data deduplication, truly understanding its power to cut through redundant data and free up valuable storage and network bandwidth, especially for those challenging remote offices. Finally, and perhaps most importantly, we arrived at the very heart of today's lesson: how all these backup concepts transform and converge, specifically in a virtualized setting, exploring both the practical pain points of traditional agent-based approaches, agent in guest versus agent on hypervisor, and the revolutionary, highly efficient image-based backup that leverages the power of hypervisor snapshots for rapid VM recovery using proxy servers. We wrapped up with a critical look at data archiving for long-term preservation of fixed content, contrasting the challenges of traditional methods with the intelligent, compliant solutions offered by content-addressed storage.
Whew. It's clear that the digital landscape is not static. It's constantly evolving, and so too must our sophisticated strategies for protecting and preserving information.
This is an ongoing battle and an ongoing opportunity for innovation. Indeed. And this leads us to a thought-provoking challenge for you, our listener. Given the relentless evolution of data and the incredibly dynamic environments it lives in, especially with the rise of cloud-native, serverless, and highly virtualized architectures, coupled with powerful concepts like immutable storage and continuous data protection, how might the traditional lines between what we've always called backup and archive continue to blur or even disappear entirely? What new skills, what new mindsets, and what new integrated approaches will be most valuable in this rapidly changing landscape to ensure our collective digital heritage remains accessible, secure, and reliable, not just for years, but potentially for generations to come. Something to mull over until our next deep dive.
Stay curious and keep exploring the fascinating world of data.
You got it.
Yeah.
We'll see you next time on The Deep Dive.